Hello viewers, welcome back to this course. So today we are going to discuss the lecture number 6, that scientific computing using MATLAB. In the previous 5 lecture we have discussed the basics of MATLAB. Now we will start with the scientific computing. So the scientific computing using MATLAB means we are taking the help of numeric analysis and the MATLAB to do the numeric computation. So in this lecture number 6, we are starting with the first one, that how the error in computations. So this is the errors in the computation, that if we do the computation using the computer, then we are generally deal with the errors because we are doing the approximation. So what are the errors that is coming up in the computation? So there are generally two type of errors. So there are two type of errors. Generally we have, that is we call it round off error, and this is the error we call it truncation error. So round off error means that suppose I have a number 10. So in the computer if I am dealing with the 10, there is no problem, there is no error. But suppose in the computer I want to use what is under root 2, or I want to use what is 1 by 3, or I want to use 2 by 3. So in this case what you will do, the computer is going to have 1 by 3. So 1 by 3 is basically 0.3333 and so on. So this is the number we have in the floating point form, 1 by 3 this one. So in the computer, suppose I take the value 1 by 3 is equal to 0.333, or maybe I can take approximate value of this 1 by 3 as 0.33333, and I stop here. So in this case I have introduced the error, that is I am approximating this number 1 by 3 into the number with 0.333. So in this case I am introducing my error, and that error will be 1 by 3 minus 0.33333. So the error will be here, I think it will be 0.0000003 and 3. So this error is called, we call it the round off error. Round off error, because in this case we have rounded off the number 0.333 by this number, and then the remaining number whatever is there, that is called the error. So this is a round off error. So that round off error is everywhere, because whenever we are dealing with a fractional, so this is a fraction, this is a fraction, this is an integer, no problem. I can use my 10 as such, but under root 2, so suppose I want to use under 2, so I will use 1.41, or maybe I can use the MATLAB, I can use its number with the 16 digit number. So in that case also, in this I am approximating the under root 2 with 1.41. So whatever the error is there, so under root 2 minus 1.41, so that is my round off error. So this error is introduced there. So that is called the round off error. And another error is the truncation error. Truncation error means suppose I have my series, maybe I want to find what is the value of e raised to power 0.001, or I want to define what is the value of e raised to power 0.5, okay, or maybe I want to define what is the value of sine pi by 12. So in this case I know that I have a exponential series for 1 plus x by 2 factorial x by 3 factorial and so on. So in this case on the right hand side there is an infinite series, and of course I cannot use the infinite number of terms to find out the value of this one. In the computation we have to truncate this series. So suppose I approximate this function as 1 plus x square by 2 factorial. Or maybe I suppose I want the more accuracy, I will take more terms. So, I will write down x square by 2 factorial or x 3 by 3 factorial, and suppose I go up to x 10 by 10 factorial. So, in this case I am approximating my function, exponential function, with 10 degree of polynomial. Now, suppose I want to find what is the value of e raised to power 0.01. So, in this case I will put this value 1.01 plus 0.01 square by 2 factorial up to 0.01 by 10 factorial. So, I am using this value for e raised to power 01 as this polynomial. So, it is a 10 degree polynomial. So, in this case I have introduced the error. So, error is what? So, this minus this. So, it means the error will be all the terms of x power n by n factorial, where n is starting from 11, not from 10, from 11 up to infinity. So, that will be your error we have introduced in this number whenever I am defining e raised to power 0.01. So, this error is called the truncation error. So, this is the one way of one example of the truncation error. Maybe I can define the another error, another form of a truncation error, like suppose I want to do the integration from a to b and this function f(x) and dx, and suppose I am unable to find the integration analytically. So, I will use the computation for that one. So, in the computer it is going to give you, because this is the way we can define. Suppose my function is something like this, and this is my a and this is my b, and I am defining this function. So, in this case what I will do, I will split this function into the number of rectangles, and then I will find out the area of these rectangles and add all these rectangles together, and then it will give me the approximate value of this integral. Or maybe, so this is suppose the subinterval, so I can take this is h. So, I can say that for a small h, if I take h, I will get some value, some approximation of this integral, and then I can even reduce the value of h, then the accuracy will increase. So, the accuracy will increase, but in all these forms, whatever the value I am taking h, so this value whatever we are calculating using the computer, it is gives you the approximate value only, because we know that if I put limit h tends to 0, only then these subintervals are going to be infinite in numbers, and only then this value will be a exact value we are able to find. But in the computer this is not possible. So, in this case I will take very small value of h, but never I can not choose the h is equal to 0. So, whatever the form it is coming, so this is also the example of the truncation error, because in this case also we are truncating the infinite number of steps to the finite number of steps. So, this is another form of truncation error. Another error, another form of truncation error, maybe I can define, suppose I have a function, derivative of the function at x naught I want to define. So, in this case I know that that is the definition of the derivative x naught by delta x. So, this is the definition of the derivative. Now, suppose I am finding the derivative with the help of computer, with the help of numeric analysis. Okay, so, in this case what we do? We just approximate this function derivative with this x naught plus delta x minus f x naught divided by delta x, and we call it where delta x is very small, where delta x is very small. So, in this case what I have done, we have value of the function, derivative of the function approximating with this factor on the right hand side, and where I am writing the delta x is very small, because delta x here it tend to be 0, but in the computer I need to find what the delta x is very small. So, I will choose the value of delta x. So, maybe I can define the delta x is 0.0001, very small value, and based on this value I will find out the value of this factor f x naught was delta x minus this, and that will be the approximate value of derivative f dash x naught. So, in this case also I am truncating, or in other form also we call it discretization error or the truncation error. So, we in this case also we are truncating the infinite number of values of delta x to the finite number of delta x. So, that is another example of the truncation error, or in the derivative form we also call it discretization error, because in this case we are discretizing the function, the derivative of the function, because here I am having the continuous form, but here we are defining changing into the discretization form. So, that is another form of truncation error. So, the question is that how this error happens. So, the main we start with that how the number is saved in the computer. So, let us start with this one. So, suppose I have a number, right. So, first I will write down the integer representation of a integer, of a number. It means suppose I have a number x is equal to 10. So, 10 is itself a representation. So, there is no approximation, and this will be saved in the computer. So, I know that in the computer the number is first changed into the binary form, and then this will be saved in the computer. So, suppose I have the number x is equal to 10, and let's so before that I just tell you that how we can change a decimal number into the binary number. So, let us start with this one. Suppose I have a number 23, and this number I am having in the terms of decimal. Now, I want to convert into the binary form. So, what I will do? I will write 23, and then this is the way I will divide it by 2. So, it will be the 11, and then the remainder will be 1. So, in that case I will multiply by 2. So, 5 into 2 and then remainder 1, then it is 2 by 2 4 and then remainder 1, then I will divide by 2. So, 2 means here I will get the 0. So, 2 1 2, that will give the 0. So, 2 1 2 and the remainder is 0, and then I will again divide by 2. So, it will be 0 and the remainder will be 1. So, I have to go till the 0 I am getting here. So, in this case this is the way we will take this one. So, the representation will be 1 0 1 1 1. So, 23 in the decimal form can be converted into the binary form with the help of this one. Now, suppose I want to find out that whether it is giving you the exact value or not. So, I can show that this is 1 0 1 1 1. So, this number I will multiply by 2 raised power 0, this is 2 raised power 1, 2 raised power 2, 2 raised power 3 and 2 raised power 4, and I am add all together. So, it is 2 raised power 4 is 16 plus it is 0 plus 4 plus 2 plus 1. So, that is 23. So, in this way we can change any number into the binary form. Now, suppose, so this is the integer we are representing. Now, suppose I have a 23. So, in this case my number will be represented by this one. Now, in the computer, suppose I have a computer 8-bit computer. So 8-bit computer means I have a memory that is divided into the 8 bits. So 1, 2, 3, 4, 5, 6, 7 and 8. So in this case what I will do, so the first one I will generally go for the sign, that this number is positive or negative, okay. So that is the sign, and the remaining part will be for the binary variables or binary numbers, okay. So in this case if I want to put 23 here, so this will be 1 1 1 0 1 0 0 and this is a 0. So this 0 is for positive and 1 is for negative. So that is the way this 23 will be saved in the computer this. So suppose if I have a 8-bit computer and I want to check what is the maximum number we can save. So in this case the maximum number can be saved is that all values should be 1 1. So 1 1 1 1 1 1 1. So it is the 7 1 and here it is the sign. So suppose I take 0, so the positive sign. So in this case the number, the maximum number is 2 raised to power 6, 2 raised to power 5, 4, 3, 2, 1, 0. So it gives you 2 raised to power 6 is 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. So add, it gives you the value 127. Okay. So it gives you the value 127. It means you can, maximum number you can save in the 8-bit computer is, and whatever that is the integer number, and that is 127. So similarly I can go for minus 127, the minimum value. Minimum number. So minimum I can go for minus 127. But the only thing is that in the computer we know that if I have to save the value 0 with the 8-bit computer, then this is 0 0 0 0 0 0 0. So I put the 0 here, so that is the 0, and doesn't matter if I put 1 here because there is no minus 0 and 0 there. So generally what we do, we add one number to the negative of the this number. So I will add minus 1, so this will become minus 28. So in this case I can say that if I work in the 8-bit computer, and so that is the number integer I can save in the computer from minus 28 to 127. So this is the number we can define. So this number I can also write as integer we can save. So that is 2 raised to power, so 2 raised to power 5 7. So this is the 7 digit 7 bits 1 2 3 4 5 6 7. So 2 raised to power 7 minus 1, so that is 127, and this will be minus 2 raised to power 7. So that is the range we can define when are working with the 8-bit computer. Similarly you can go for up to 16 bit. So in the 16-bit computer, so this integer range it will be, so 15, so up to, it will go to up to 15 minus 1 and minus of 2 raised to power 15. So that is the range we can define for the 16-bit computer. So these days we are working with 32-bit or the 64-bit. So accordingly you can check for the 64-bit computer, the present computer. So it will go to up to 63 minus 1. So that is the range. Minus of 2 raised to power 64, sorry 63. So, you can see that a very big number we can deal with at the present computer. So, that is how we can define the integer. Now, the things comes when we deal with the floating point. Floating point representation. Of a number. Like I have 0.75. So, that is given to me in the form of decimal form, and I want to convert this one into the binary form. So, integer we know, but in the fractional part, suppose I have 0.75, then how I want to convert this one into the binary form. So, what I will do, I will multiply this by 2. So, it will give me 1.50. So, I will keep this fractional part, and again I will write 0.50 into 2, and now it gives you 1.00. So, this fractional part is 0 now. So, this is the number we can say, and by this way we can calculate. So, it gives me 0.11. So, it means 0.11 gives me the value in the decimal form for this 0.75, and how I can verify, because I can convert this one. So, it is 0.11. So, this will go to 2 raised to power minus 1, and this will go to 2 raised to power minus 2. So, it will give you 2 raised to power minus 1 plus 2 raised to power minus 2. So, it is 1 by 2 plus 1 by 4. So, that is the 3 by 4. So, 3 by 4 is 0.75. So, that is verified. Maybe I can, so this is the function value of the 0.75 decimal form into the binary form. Maybe I have some another number 0.4, that is in the given to me in the decimal form. Now, I want to convert this one into the binary form. So, what I will do, I will write 0.4 into 2. So, that gives me 0.8. Now, I will find 0.8 into 2. So, that is 1.6, then 0.6 into 2. So, that is 1.2, 0.2 into 2, that is 0. So, I can put 0 here. So, 0.4. So, 0.4 came again. Now, I write 0.4 into 2. So, it is 0.8, sorry, 0.8, and then the same thing will repeat again and again. It means this is the binary form we can take. So, I can write from here that it will be 0.0110, then again 0110, then again. So, this is the recurring relation, and that is the representation of 0.4 in the decimal form to the binary form. So, from here we can see that 0.4 is truncated value, but if I convert this one into the floating point into the binary form, then this is the recurring relation we are getting. So, that way we can define we can convert the function in the decimal form, a floating point in the decimal form to the binary form. Now, we are dealing with the floating point representation of the number. So, how we can do that? So, in the floating point, suppose I have a number x. So, this is a representation, it can be a positive and negative, and I will represent by s multiply by d and then e. So, that is the floating point representation of a number in decimal form or in the binary form. So, what is this? So, that is the sign. This is what? So, this is called significant or mantissa. So, that is gives you the significant or mantissa. This is, so that gives you the decimal. So, this is it can be a, what we call it, decimal part or binary form, okay, and that is the exponential part. Exponential. So, in this case I can present any number. So, suppose I have a number x is equal to maybe 23.75. So, this number we can write as, I can write this number as 2.375 maybe multiplied by 10. So, in this case this is the power is 1. So, that is the number we have. In this case the same number, if somebody asks me that write the same number, so this number can be written as 10 raised to power 0. The only thing is that here we are putting this number, so we have a 2 digits before the decimal, and in this case we have 1 digit before the decimal. So, in this case we have to define that what is the basically a well accepted form of the number. So, that is called, what we are doing here is, that is there are 2 forms are well accepted by all over world. So, that is, first one is the normalized form, and another is scientific form. So, normalized form is that the value of s, so this the value of s is always lying between 0.1 to 1, and this, in this case its value is from 1 to 10, less than 10. So, this is the normalized form and this is the scientific form. So, in this case 2.375 into 10 to the power 1. So, if I have this one, so this form is not a scientific form or the normalized form, because here the value of s is 23, right. So, it is not falling any of the category, but in this case I can say that this is the value of s, and this value is s is lying here between 0.1 to 1, sorry, from 1, it is 2.3. So, it is lying between 1 and 0. So, this is a scientific form. Now, the same number I can write x is equal to 0.2375 into 10 raised to power 2. So, in this case my s number is now, this is my s, so it is 0.1 to 1. So, that is the normalized form. So, in the normalized form we put all the digits, whatever the non-zero digits are there, on the right of the decimal and raise the power whatever is needed. So, that is the normalized form of the value x. Maybe I take another value of x, suppose I have a number 0.00452. So, this is the number we have the real number or a floating point number. So, this number I can write in the form of, so what I do, so these are the 3 zeros, this is unnecessary 0. So, I can write this number as 0.452 into 10 raised to power minus 3, because I have taken this dot to the 3 on the right hand side. So, I have to multiply by this 10 raised to power minus 3. So, that is the normalized form of this number. In this case my s is lying between 0.1 to 1. So, my s is lying 0.1 less than 1, and this is the exponential we have. So, in this case I can say that this number is in the normalized form, and this is significant, means it has 3 significant digits. So, that is the normalized form of the decimal number. So, today in this class we have discussed about that how the two type of error comes to the computer whenever we do the calculation, there is round off error and the truncation error. And then we also discussed that how we can convert a decimal number into the binary number, which is used when we are dealing with that how the number is allocated in the computer. So, in the next class we will go further with this one. Thanks for watching. Thank you.